Welcome to this IRIS-HEP topical meeting. It's being presented by Chen from UC Chicago, accelerating raw data analysis with ACCORDA. So please, Chen, the way we usually do this is if people have pressing questions, they may try and interrupt, but let's leave most of the discussion for the end, if possible.
Yeah, that's my point. Thank you. Well, thanks for the introduction. Thanks for everyone coming to my presentation today. I present our work on ACCORDA, accelerating raw data analysis. First, I guess everyone must already be familiar with the notion of analysis as the process where we derive answers from data by specifying a sequence of manipulation and processing on the data. Here, the data are usually organized in the table formats and structured with index and schemas for efficient management and querying the traditional database management systems. However, with the growth of big data and IoT technology, we see the rise of data lake where the data stays in its original, unorganized, unstructured form. We call these raw data. They reside in formats that's not optimized for analysis queries. And traditionally, the process called ETL, extract, transform, and load is required to transform these raw data into suitable formats for later analysis. In some sense, the different variants of the AOD data is also partially raw data, although there are some optimizations for analysis. For example, there are columnar support in T-branch data structure. The data transformation and reconstruction are still needed if we want to analyze the data stored in those formats. The traditional way of handling these raw data for analysis is bulky and time-consuming because of the extract, transform, and load process. All the data in various formats need to be first transformed into the optimized formats for analysis of the corresponding database management software before any analysis could be performed. This makes us wonder, can we directly analyze the data in its raw format, getting around that ETL bottleneck? If we can do faster analysis on raw data, there are several new capabilities possible. First, fast raw data analysis would enable interactive analysis and thus reduce the time from data to insights. Further, diverse open data structures could be supported as the data that can be analyzed are not restricted to reside in one canonic format anymore if we have fast raw data analysis. However, despite we can do data transformation on the raw data that are only necessary for the query rather than doing bulk ETL that transform and load all the raw data into a database management system. The corresponding pre-processing for the raw data we are only interested in are still time-consuming and expensive comparing to execute queries on the loaded data in the database management system. In short, the naive way of doing raw data analysis would suffer from data transformation bottleneck. The usual approach to address this data transformation bottleneck is to employ accelerators. After all, this golden era for accelerators as Dana scaling and Moore's law are all dead now. But it's easy to fall in this what we call acceleration pitfall and causing huge disruptions in database management software. As one would imagine, an accelerator would potentially need separate memory management, scheduling, and runtime management, including the software architecture of the original database management system. Here, we propose ACCORDA. This is our approach, which addresses the challenges in both software and hardware perspectives. In software aspects, the ACCORDA preserves the traditional database management system software architecture and thus minimizing the software disruptions. In hardware, we develop an accelerator which enables fast in-memory hierarchy acceleration, addressing the data transformation bottleneck. Let's first look into the software architecture design of ACCORDA. Towards the goal of enabling optimization and acceleration over data encodings and transformations, as well as minimize the accelerator's disruption on software architecture, we made two design choices. First is to extend the database management system operator interface with encodings, specifying the formats the data residing. And second, we also opt for an uniform runtime workers to minimize the disruptions on the runtime schedule. First, the operator extension. To deal with the raw data, the operator attribute is actually augmented with the field that's describing the encoding, the raw data, or the processed data is in. This enables the data management system to consider both the costs and the benefits of handling the data in the specific formats and the data transformation involved when performing different query optimizations. Further, by introducing the encoding in the interface of the operator, it exposes two opportunities. One is the lazy data encoding, and the other is the encoding solution. Essentially, data transformation doesn't need to be handled at the loading phase of the analysis, at the data loading phase of the analysis. For example, the sorting on an ordered dictionary encode string is much cheaper than sorting directly on the strings themselves. By extending the formats into the operator interface, it allows the database management software to consider what kind of operations are cheaper to do in certain formats, and the database management system could exploit different ways to perform certain operations. And the second design choice we made is about this uniform worker model. Because the size and power consumption of the traditional accelerator, which you can think of GPU and FPGA, they are usually huge, and that enforces a separate and diverse worker model in the sense that CPU and the accelerator are treated by the software as disjoint computing resources, as this large accelerator usually reside off-chip on the, for example, PCIe bus. This is actually where the aforementioned accelerator pitfall originates. With ACCORDA accelerator, which is fast and tiny, as we would discuss later in the hardware architecture design, it enables the in-memory hierarchy integration, enjoying the low overhead data sharing. This enables us to employ a uniform worker model that minimizes the disruption on the runtime scheduling of the computations. The disruptions from the acceleration is minimized. The two design choices we just described on the software architecture side avoid the acceleration pitfall and preserve the software architecture of the traditional database management. There is no need to adapt the layering we are showing here from the original database software into an accelerated version, as they are essentially the same. Moreover, our design choices preserve the query optimizer, which is a very essential part of the data management system. Other accelerators with large physical area and high power, and which enforces an PCIe integration and a heterogeneous work model, would require the database management system to develop the separate operator device scheduler and different strategy optimized for that kind of accelerators, polluting the software architecture, where in our ACCORDA, thanks to the two design choices of the software architecture, we made the core optimized architecture is the same. All we have to do in ACCORDA is just to extend some new cost models of the accelerated operators and the optimization rules under and the optimization rules for these accelerated operators. And these extensions are all done with the existing framework of this cost model and optimization rules, the database management already built. So that's a huge gain in software efforts. Now let's discuss the hardware architecture and designs. The first question we look at is actually where the accelerator should sit. There are generally two approaches, and we actually touched them in previous discussion. We can put the accelerator off chip on the PCIe bus, or we can also put the accelerator on the chip integrated with the memory hierarchy. Because we require that lower overhead data sharing to minimize the software architecture disruption and enable the uniform worker model, we opt for the in-memory hierarchy integration. In our model, actually, the UDP resides on the cross buses between the L2 and LLC. To enable this kind of integration, it requires the accelerator here, UDP, to be small and low power. And because it interrogates on the CPU chip, we can't, you can't swap in another one if you find the acceleration function you implemented isn't general enough. This would require the accelerator to be general and support current and future model, as opposed to a fixed function acceleration implementation. This accelerator is actually we call unstructured data processor, which is from our previous work. It features the efficient branching through multi-way dispatch, which is enabled by controlled program layout. Because the data transformation task is actually pretty branching intensive, this accelerator drastically improves the data transformation performance by 20x in terms of pure performance and 100x in terms of energy efficiency. Further, it is low power and area cost, which meets our previous requirements for in-memory integration. This accelerator is only 100% in terms of area and power cost, comparing to a 8-core Skylake SP CPU, so that it can fit in the memory hierarchy. Moreover, the UDP is highly programmable as an application-specific instruction set processor rather than a fixed function ASIC. Its SI is designed to efficiently support the relevant data transformation workloads. And we developed the whole compilation toolchain for it, so it could support different kinds of present and future data transformation tasks, as if the function unit to accelerator changes, you just need to reprogram the accelerator going through this compilation process. Now we will discuss our evaluation on our ACCORDA approach for fast raw data analysis. The workload we considered are all queries, all the 22 queries from TPCH, which is a decision support benchmark. The data for these queries resides in raw tabular formats, which is very similar to comma-separated value format. The ACCORDA software framework is prototyped on the Apache Spark, and we use the Xeon FPGA platform, which has a FPGA chip soldered onto the CPU socket to emulate the ACCORDA accelerator. We call it UDP, and the in-memory integration of the UDP into the system. We opt to use a hybrid timed simulation approach for the evaluation. This is to compensate our performance loss between the FPGA implementation and the ASIC implementation. As you can see, the performance differences exemplified in the table here. Specifically, we collect the Spark worker trace for each query and retime the accelerator portion to consider the transfer time and the UDP compute time differently. We need to scale the UDP performance from the FPGA number into the ASIC implementation number, as shown in the table here. Now let's look into some performance figures. Here, in this figure, there are two performance baselines. First is the traditional process of doing bulk extract, transform, and load on the raw data into the database optimized formats, and then perform the queries. That's the batch ETR showing the blue bars here. And the second red bars are corresponding to ETR on-demand ETR, where you only extract, transform, and load the tables that are necessary for the specific queries. As you can see, the batch ETR is more expensive as it bulk loads all the tables, where on-demand ETR only does the ETR process for the necessary tables on the raw data. These are two performance baselines. And if we add the the early filtering, which is from the previous framework, previous research work called Sparser, it does the filtering on the raw data without parsing it. If we can further reduce the data on the raw data, if we can further reduce the raw data to be pre-processed to be data transformed into the database format, it would reduce the cost of doing the data transformation, but it only does that by a little, as the support of the Sparser on the filtering is scarce, and the core of the problem is not addressed. Sparser only reduces the data to be pre-processed, but not accelerate the pre-processing process. And here comes our approach, which is ACCORDA. ACCORDA essentially address the core problems of the raw data pre-processing. By employing accelerations in reconstruction and transformation, it robustly improves the raw data analysis performance by 16x comparing to batch ETL, 4.6x comparing to the on-demand ETL approach, and 3.6x comparing to the previous method, Sparser. Further, we also compare the ACCORDA approach on raw data analysis with the cached analysis. This is essentially where the data are already. We are comparing the ACCORDA performance on raw data analysis versus the database management system analysis performance with loaded data. So the ACCORDA is actually doing more work doing the data transformation workload. Essentially, ACCORDA ACCORDA significantly eliminates the raw data processing overhead and approaching that ideal case where all the analysis are performed on loaded cached data. And there is only a 20% performance margin between them. In summary, our ACCORDA approach preserves the database software through encoding extended operator interface and uniform runtime worker model, delivering fast and robust raw data analysis, which matches the performance of the ideal case, the analysis on loaded and cached data. There are also the other contents in the paper which may be interesting for you to look into. I will just bring out them here. There are performance sensitivity study on filter selectivity and raw data complexity, and there are also comparisons between the FPGA and the other accelerator approaches. This is end of my presentation. I'm happy to take any questions.
Thank you. So let's see. I guess why don't we start with questions from video?
From video? I'm sorry, I'm not following.
No, I'm sorry. We often start with questions either from the room or from remote conferencing, but of course, right now everybody's remote conferencing. So I just wonder if anybody's got a question, and perhaps while they're thinking up thinking of a question they would like to ask, I wanted to know a little bit more about the unstructured data processor, this UDP. Is this just a chip, or is it something custom designed there, or is it was this micro 17? Yeah.
It's an application specific instruction set processor. We had a ASIC implementation, so it's designed to be tape out on a silicon, but we never actually go down through that though to tape out this chip. In terms of integration, we think there are different opportunities. It certainly could serve as a chip on the PCIe bus, like GPU and FPGA, but because it is small and low power, we think more benefits can be achieved if we integrate it in the memory hierarchy. Essentially, you need to piece together the hardware description language code of UDP and CPU to explore that benefits. I'm not sure if I explained.
So for example, like with an ARM processor, you'd put it on the same piece of silicon as the ARM processor. Lay them out together, something like that.
Yeah,
okay,
yeah,
that's
right.
And so, I don't know if I completely understood the first part what you're saying. So, is this a simulation where you're measuring its performance, or that you actually have silicon upon which you use this?
We implement it on the FPGA. We implement the accelerator on the FPGA. So
on the FPGA, perfect.
The scaled down performance, because FPGA frequency is much
so here instead of 30, you're getting 3 gigabytes a second, and okay, perfect. Right.
Yeah. There are differences in data transfer performance because the closer integration thing, and there are differences on clock speed because FPGA doesn't clock that well. Yeah. And for the performance number, we scale the FPGA number by 25 times.
Okay.
So the results you see is actually corresponding to the ASIC implementation.
Or what? I mean, you've not done an ASIC implementation, is that right?
Yeah.
So
yeah.
So this is based on simulation. Okay, perfect.
Yeah.
All right. Other questions or comments from folks?
Gordon, could I interject? This is Andrew
Please.
Chen. I just wanted to add, I put it in the chat, Chen has been working on follow-up work that takes the same sort of UDP and explores the extending implementation of that into stored controllers in this context of computational storage. I know some people on the call have heard about that, but the idea is similar techniques could be used on the storage side because the UDP is quite a small, inexpensive piece of silicon, and that could have a big impact on both this kind of data analytics, but we hope also a broader array of HEP kinds of computations.
How complex a query manipulation can it do?
Chen, do you want to field that one?
How complex? For the because we have this. Let me see. Because we extend the operator interface with this encoding format, it actually the support is pretty general. Like, I'm sorry, are you asking the software? I will describe it in both aspects. In software, the possibility is pretty unlimited because it all depends on the cost model. Like the database query engine would ultimately choose the best available operators and query plan based on the extended operator and the extended operator cost models. In terms of hardware support on this kind of transformation, we believe the support is also pretty general, and we can do half-man encoding, different kinds of encoding, in half-man dictionary, compression, decompression in terms of snappy and RJ77 related compression. I think, and we can do different kinds of parsing and filtering on the predicates and column selection, this kind of workloads that's common for the raw data analytics.
Right.
And since we have an ESA, it's not fixed function. Like you can always extend the functionality by just writing a new piece of program.
Right, because the unstructured data processor can effectively be reprogrammed on the fly.
Yeah, yeah.
Okay, thank you. Was somebody else trying to add something or follow on to that question? I thought I heard another voice right in the middle of Chen's answer. Okay.
Go ahead.
Please go ahead.
I was just going to say, one way to think about your question, Gordon, is that we designed the UDP to be very general across data transformation kinds of tasks. So scanning, parsing, transformation kinds of things. It wasn't designed to be a heavy computational engine in the sense of, floating point operations, numerical simulations and the like. It would be possible to add a small amount of that, but it really, isn't intended to compete with the GPU or something like that in that kind of floating point computational power.
Right. I was thinking more along the lines of, some of the filtering operations can get fairly complicated. Looking at joins, looking at properties of counts of joins and things like that. And that was more what I was interested in. So I think it would be right along the lines of a query, but it might contain some fairly complex relationships that you're going to be querying over.
I think that's all in scope. Yeah, I think we believe all those things could be supported.
Awesome. All right. I should shut up and let some of the other 19 folks make a comment or ask a question.
Yeah, very great talk. This is Carlos Marzan at UC Santa Cruz. So I was wondering if you spread data across. So I'm very intrigued about hearing that you thinking of integrating UDP into an SSD. If you have multiple SSDs and you stripe the data across multiple SSDs, what happens if you will have to sort of align the data so you could analyze the data within the SSD, right? So you don't have like complete records from So it has to be like logically aligned. Have you thought about this, or is it something that you're working on?
Yeah, it's actually something I'm considering and working on. Like I believe this problem is pretty general as like any kind of HDFS kind of workload would have like logical records separated across the different nodes, and the method is also general as well. We just need to transfer messaging the pieces from the of at the starting, messaging the partial pieces at the starting of one block to the engine that's handling the previous block, right? There are some properties that involving whether this could be done efficiently, like how large is the block and how large is the logical piece. So there are some criterion there in order to do this efficiently, I believe. That's what I'm thinking. I don't know.
Yeah, it's interesting. That's so that basically means sort of it's just grabbing the aligning on the fly, if you will, right? So you versus maybe placing. You could also think of like a rate-like controller, right, where the actual UDP sits in the rate controller, and you would write and read sort of in an aligned fashion, because but that would require that you always have that you do the management of or a set of storage devices, with a common controller, which has advantages and disadvantages too. But yeah, I mean, yours sounds more general.
One question for me: when it comes to commercial solutions, what are the best known ones?
I'm sorry.
Do you know about commercially available solutions for this kind of approach? Like I remember even a long time ago, Oracle had its own SSD accelerated, developed together with Intel and everything.
SNA have a technology forum on computational storage. There are a lot of vendors presenting their R&D process there. I couldn't name the names there, but there are a lot of them on that SNIA forums.
Way to answer that question as well. Let me just chime in. This is Andrew. There are a bunch of folks for this kind of raw data analysis who've been pushing software techniques, and you've seen some of the software techniques compared directly. There are also folks who are putting FPGAs into storage controllers, probably more storage controllers than SSDs, and then integrating those operators on the storage controller side into systems like Spark to do special case kind of optimization and so on. But they represent sort of a near-term compromise, right, for what is capable in terms of hardware architecture, in terms of performance, and often they are works in progress, very hard to track because they may not even be a fixed product. They'll just change over time. The Oracle thing, I'm not familiar with the SSD embedded acceleration, but Oracle built a very aggressive system called Sonoma DAX, which was a Spark-based acceleration system, almost all on the processor side, where they implemented a number of special hardware accelerators. I think they had 8 or 9 of these things that did compression and transpose and filtering and so on. So that was sort of an all-in customization. I would call that a 10 by 10 architecture if you follow, the work we've been doing on customization and architecture for databases. But the 2 problems with that, I mean, one is the database appliance business isn't going so well. So I don't believe that design actually is, being promoted by Oracle so much these days. But the other is that the problem is all of those operations are subject to improved algorithms, right? And the use of these hardware ASIC blocks that were not programmable actually limited the kind of compression, limited the customization, and the other kinds of things that they could do. So they, had a benefit, but it's a fragile benefit as you advance the database design.
Okay.
Perhaps there are others that know about things that were done as well.
Are there other questions or comments?
I guess a related question is, Andrew, is like, what would you see as sort of like the timeline for any kind of, commercial / well, I guess you really couldn't call it commodity at this point, but any kind of system that, could potentially, we could potentially purchase and have some kind of capability that does some of the things here that Chen was talking about. Like, how far away are we,
Chen, do you have to say a few words about what's happening with computational storage in the Flash community and the SIA cemetery, what those folks are doing? Because I think it's actually moving pretty fast. And we could talk about that, and then we could talk a little bit about what it would take to get something like UDP into some of those products, right? But first, the baseline. And Carlos, I think, too, if he wants to chime in. Go ahead, Chen.
Yeah, I think a lot of companies are developing their products. Like Samsung has a smart SSD, and the ARM is also pushing hard on like doing like computational storage device management and identification management and that kind of processes. I think the industry is forming a standard, but that's still a work in progress. I guess the next step I'm looking forward to is actually the standard for it, similar to what they do for like NVMe or something similar. So
yeah, I think those standards are coming. I think there are pre-standard products, and there will be various things available that comply in part or in whole with the standard. It all depends on how aggressive one wants to be, but those are mostly lower level primitives or relatively static customized operators, I think is what we're seeing. But others may have more insight.
If I can add to that, I think that, yeah, I agree. There's currently very much a focus on on individual devices having capabilities, right? And yes, there is, I think, definitely. I mean, based on my conversations with some of the industry players, is they definitely want this to be programmable. They know that any kind of fixed set of operations is going to just put them into a trap, right? You invest into a lot of silicon, and then you have to throw it away because something better comes along. And so it's not clear at this point how they are going to deal with collective behavior of devices, which I think will eventually have to happen, right? So a lot of them see through this, because of disaggregation, that these devices are going to be connected to some kind of full crossbar network. So the devices could talk to each other, for instance. And I think that's when it becomes interesting. But I think that's not really that much talked about at this point in those groups. It's mostly just per device functionality, and then anything that is across devices is sort of on a layer above that.
Speaking of this, Carlos, let me pick your brain. There are some companies like, Pure and, maybe NetApp to some degree, right, that are in the storage system business, right? So they have an insertion point for acceleration across multiple devices, right? I'm curious, if you see them and perhaps ARM or other kinds of accelerators doing something interesting in this space.
Well, NetApp is very engaged in SNIA, in this computational device, in fact, I think the whole editing is actually led by NetApp right now. So they're obviously very keen in having these computational devices and see an opportunity to put them together and present them in interesting ways to the application. I don't know, of course, I don't know much about what Pure Storage is doing, but I do know that they're probably would like to have a role still in outside computational storage devices. I don't know. Maybe they have also plans to buy some of these startups or something. I don't know. That's hard to tell.
They and NetApp sit at this sort of storage system controller level, so they have a natural insertion point across multiple storage devices for accelerated functions.
Yes, yeah. But I see that mostly as a software business, right? That's basically, I don't know. I mean, I think that traditionally NetApp is doing is basically refitting standard server technology into high-end storage servers, and so they, I don't know what their new plans are, obviously, but I think that's there could be also accelerators in that as well. But I think sort of in the computational storage device, I know that there's a number of companies who are interested in actually eventually having storage devices to act collectively. And I think that's really interesting. That's also interesting for us.
Yeah, that'd be very cool. Let's see. Any other comments or questions? Going once. Okay. Chen, thank you so much and Andrew for your time and the presentation. I see the slides are now uploaded, so we can get them later. And we will also make this recording available on our YouTube channel. Take care, everyone.